Good morning, guys. So, in the last part of the lesson, this is a bit of a long lesson. So in the last video, we looked at systems, a linear system with two variables, and we explored the three possibilities. One, there's a unique solution. Two, there are no solution. And the third one is that infinite solution. And we saw that it's all about lines intersecting, okay, overlapping or parallel. Now our mission is to look at a linear system of three variables, x, y, and z. Now, as with the two variables, I'm going to start with just looking at systems and not thinking about geometrically what they mean. And I'll be honest with you, that is really the thing that you need to know for the test. So I looked at some exam questions, and so the first part of this lesson is the one you really need to know. And then we're going to move to more fancy stuff, which is, I haven't seen any exam question, but it's nice. So we'll do it, but don't worry about it too much. So I've got three linear systems, okay? And what we're trying to find out is how many solutions they have, okay? Again, do they have a unique solution? Do they have no solution? Or do they have infinite number of solutions, okay? So we'll start with the right. So we've got a linear system. So the first thing to do is really to find the determinant, or not to find, first the matrix of the coefficient. Okay, so it's going to be 2x plus 3y plus 4z. It's 2, 3, 4, 3 minus 2, 5, 1 minus 2, 3. Okay, that's your matrix. Okay, now the first step to do is, if this is the matrix, is to find out the determinant of the matrix. Okay? So in this specific case, when it's all numbers, okay, we'll talk about another situation when it's not all numbers, but if it's all numbers, you just use the calculator. Definitely use the calculator. And what you'll find out that you get a determinant, which I don't know what it is, but it's not 0. Okay? So it's definitely not 0. All right? And red. So if its determinant is not 0, we know we're going to have a unique solution. Okay? And then they might ask you, all right, find the unique solution. Okay? And in this case, personally, I probably will, or you can either use the calculator to find the inverse matrix, which is probably the right thing, and then use that formula with that joint to find the solution. But the way I did it, and I'm not going to do it now, but I'll just show you, the solution is by row operation. So remember, what we do is we augment this matrix now. 2, 3, 4, 3 minus 2, 5, and 1 minus 2, 3. Okay, and I augment, I add the column of the solutions, 5, 1, 4. And then what I need to do is start row operation, until I turn it into a reduced echelon, row echelon, okay? I'm not going to do it in front of you now, but I'll just show you what happens when I did it. So I got 2, 3, 4, 5. The first row is the same. And then I have 3, not 3, I had the 0 there. I want the 0 there, obviously. 0, 4, minus 4, and minus 11. And then I had 0, 0, and minus 20 over 7, minus 65 over 7. Okay? So that's what I had, and we had a whole lesson about what are the solutions. Okay, so this is times z equal that, so you can find what z is. Then you use this line to find what y is in terms of the z that we found. And this last line will help us to find what x is. But what I want you to focus on now is that, well, we'll just look at that row, okay? So I have 2 zeros and a number and a number, okay? You'll see why I'm referring to it in a minute, okay? I didn't write the solution, but we definitely see that there is a unique solution. Now let's move on to the next one, okay? So I will first start by writing the matrix. Okay, the matrix is 2, 3, 4, 2, 3, 4, and then minus 1, 3, 1, 4, 6, 8. Okay, that's the matrix of coefficient. And if I want to find the determinant of that, what will happen if you fit that in the calculator actually is 0. Okay, so it is 0. Okay, here the determinant was not 0. Here the determinant is 0. Okay, so now we know from the two variable case is that there's two options. Either there is no solution or there are infinite solution. Okay, so our job now is to decide, is there a solution? Is there infinite solution or no solution? So I need to do the same thing. I'm going to do row operation. I think that's probably the best thing to do. Again, I've done it before, so I'm going to save us some time. I'm going to write down the answer. Okay, maybe I'll just take you through what I've done here. So I'm going to use the same method of the row operation. Okay, so I'm going to write the same matrix. 2, minus 1, 4, 3, 3, 6, 4, 1, 8. I'm going to augment, add 5, 1, 10. Okay, and I'm going to make row operation. Maybe let's get rid of this line. Okay, and I'm going to turn on row operation. And what I've got after all that work, which took a while, 2, 3, 4, 5. Send them a bit there. I got 0, 9, 6, 7, and then I've got this. Okay, that's what I want to look at. Okay, so when I start reducing the rows, I end up having a row of 0. Row of 0. Okay, now I got to think, what does this row of 0 mean? You remember that, let's just actually write down what that means. Okay, so this, I'll write down the first row. Okay, so remember that we multiplying this matrix. Okay, this row tells us that 2x plus 3y plus 4z equal 5. This row. The second row, we got rid of, that's why we got a 0 here, because we eliminated x. So this one says 9y plus 6z equals 7. Okay, all good so far. But what does the third row say? Okay, 0x plus 0y, well, the last number should have been a number, like here. Should have been something times z. But what it says is 0z equals 0. Well, 0 times z is obviously 0, so 0z, z could be any number. Can you see that? Oops, can't see that, so I'll move it down a bit. So the last row really doesn't fix the z. Okay? This row fixes the z. It tells us that minus 20 over 7 z equal minus 65 over 7. So that allows us to find what z, and then the rest of the rows could help us find what the x and the y are. But here, 0z equals 0. Well, any z will do, right? If any z will do, that means I have infinite solution. Okay? Any z will do. Then, if I chose, let's say, z1, okay, then I'll put z equal 1, and then I can find what the y is, with that z equal 1. And then once I know the z and the y, then I can find the x. Okay? So I've got what you call later on in university called 1 degree of freedom. Z could be anything, and y and x will determine according to it. Okay? So in other words, a row of zeros, and including a 0 here, that means that there is infinite solutions. Okay? I'll just highlight that because that really is the most, writing and really the important stuff. Okay? So when I have, and like I've done so far, okay, I don't have a row of 0, that means unique solution. Okay? When I have, in this case I had determinant equals 0. Okay? So at this point I don't know if it's infinite or no solution. When I try to actually solve it and I have a full row of 0, I get infinite solution. Okay, let's move on to the last one. I wonder if you guys can see it. Oh, I think you can. I'm just going to stand here. So I've got one more system. Okay, if you don't mind, I'm not going to even write the matrix here, but you probably will just have to believe me. I'll stand here. That the determinant in this case is also equal to 0. So So I took the coefficient, the matrix, the coefficient, put them in the calculator, determined with 0. So at this point, again, it could be that there's infinite solution, or you can probably imagine in this case there's going to be no solution. How do we know that there are no solution? I want to see what it looks like. Okay? So I'm going to write the augmented matrix. You're not going to see me for a second. It's just easy to stand here. So minus 1, 3, minus 5, and 5. Can you see the minus 1? Don't know. Move you a little bit there. Yeah. Okay? And then you've got 2, minus 6, 10, and 10, and 2, 6, 4, and 4. Okay? And then at this point, we're starting to do a row operation, adding rows, subtracting, multiplying, until we try to turn it into something that looks like this, reduced row echelon. But what happened in this case, when I was working on it, it came out like this. 2, 3, 4, 5. Okay, that was this. Oh, I should really write an arrow. Okay, so I did a row operation and I got. No, I got that one. Sorry, wrong one. Minus 1, 3, minus 5, and 5. Then I got 0, 0, 0, 17. And then I got 0, 7, 6, 0. Okay, what does that mean? Okay, I've got my row of 0. Whenever I have a row of 0, you know that there is, you'll see later, I'll do a video, whenever there's a row of 0s also, it means that the determinant is 0, but you know there is no unique solution. But the difference in this case is that it's not complete row of 0. On the other side, the solution, the augmented bit, is not 0, it's 17. So let's try and write down this row in terms of the variable. What color did I do it before? Okay, so I'm just going to stand here. Okay, so this row means that 0x plus 0y plus 0z equals 17. Okay, alright? Can that be? Okay, are there any x, y's, and z? Whatever I choose them, if I'm multiplying by 0, surely I get 0. But on the other side of the equation, I got 17. 0 can never be 17. So in this case, we have a no solution. Okay? Where am I going to write it here? Okay? Just write it here. So I have no solution. I'll just write down no solution here. No solution. Okay? Alright, so I'm just going to summarize this. This is really the most important bit. Okay? The fancy stuff will come now, but it's not as essential. Yeah. Alright, so if you've got a system, linear system, first of all, write down the matrix. Use the calculator, if you can, you'll see in a second where we can't, okay, to find the determinant. If the determinant is not 0, no problem. You've got a good well-behaving system. That means you have a unique solution. And if you need to find it. If the determinant is 0, okay, now in that case, there's two, at this point, either there's infinite solution or no solution. What do we do? Best thing to do is just row operation, reduce the rows, get as many zeros as you can. If you end up with a row of 0, but a number on the other side, no solution. If it's a full row of 0, infinite solution. That's it. Okay? I'll pause, make some space, and then we look at a typical exam question that I've seen. Okay, I'm not going to solve the whole problem because this video is going to be already too long and we have that other video. Lesson is getting really big. But when I looked at the type of questions that you have in the exam, they often will be like this. So you'll have a system, a linear system. We've got variables, x, y, z. We've got numbers, but we also have like 2 more variables, t and w. And what the question that they would ask often is, for what value, they will start like this. For what value of t, we will have unique solution. Okay? And then then what you got to do is, okay, I drew out the matrix. That's the matrix of the coefficient. I already augmented it, but for the first part, you'll just need the matrix of the coefficient. And we know that unique solution, really, the determinant must not be 0. So then we write down an equation, okay? Right, we find the determinant. Okay, here we can't use the calculator, right? Because 1, 2, you know, I've got a t here, so I can't put a t in the calculator. So I'll have to write down, you know, find the whole way, maybe use a clever row, probably use this row. 1 times its minor plus t times its minor. You'll have and make it not equal to 0, or find when it is equal to 0, and all the rest of the value, and then you'll have an equation of t. Okay, I mean, we can do it quickly, but I'm not going to do it. You know how to do it, okay? It's going to be 1 times the matrix, the determinant of this, plus t times the determinant of this one, adding the cofactor, make it equal to 0, and the values of t that will give you a determinant of 0, that's going to be not unique solution. So any other values of t will give you a unique solution. Now, then the next question, they might say, for what values of t, for example, there will be no solution. No solution. So what we got to do then is take the augmented matrix and do row reduction. And again, I'm not going to do it here because that's going to take us too long. But you'll have, the first row will be the same. The second row will have a 0 and, I don't know, a bunch of other stuff, numbers. And then the last row, you're going to have 0, 0, and then you're going to have here something with t. Okay? So you did the row operation, I don't know what you get. I'm going to write down something. Obviously, it's not the right thing, it's just a guess. But let's say you have 3 minus t. I don't know. It's not. It's going to be more, but it's something else. 3 minus t over 2, let's say. Okay? And here, you're going to have to also do whatever you do to these numbers, you have to do to w. You might have 2w plus 1. Okay? So you basically just went through the process. And now you got to say, okay, to have no solution, okay? To have no solution, then I need t, first of all, this need to be 0. Okay? So to have no solution, then 3 minus t over 2 equal to 0, I find what t is. But that's not enough. That will turn this to 0. Okay? To have no solution, I need this number to be non-zero. So also 2w plus 1 is not equal to 0. That will give me a no solution. If I want, then they ask me the same thing, but now I want to have infinite solutions. Then again, the t, this thing still needs to be 0. But now this one you want also to be 0. Then you have infinite solution. Okay? So that's the kind of more difficult question I find in the exams. Right, I'm going to pause here and we're moving to the next part of this lesson where we're trying to find geometrical representation of having unique solution, no solution, and an infinite solution. Okay, so my first step is to try and find out start here. Let's go back to our two variables. The equation with two variables. Have x plus 2y equal 3. We spoke about it, and it's not a secret. You knew that before. That graphically, that means it's a straight line. Okay? If I move the x to the other side, it'll be minus x, so it's a straight line with a negative gradient. Never mind about where they intersect. So now the question is, what about if I have an equation now with 3 variables? Because that's what we're working with. What does that mean? Equation with 2 variables is a straight line. What's an equation with 3 variables? Now, if you think about it, what we're doing, we're just adding one more dimension. So instead of having a straight line, we're going to have, okay, a flat or a straight plane. Okay, it will be a plane. Okay, now I'm going to try and convince you. There's a couple of ways of doing it. I'll do the one that I think it's the easiest. So we're going to write, I've got this, okay, I've got 3 variables. I think this is maybe the first time you're seeing a Cartesian axes with 3 variables, okay? 3-dimensional space. Now, to see that this thing is really a plane, what I would say, okay, let's choose, let's write it down but now we'll restrict z equals 0. We'll make sure we're only working with z is equal to 0. So in this case, we're going to write it as x plus 2y equal 3. Well, right, because z is 0. But what is x plus 2y over 3? We know it's a straight line on the xy plane. Okay, so I'm going to just draw a straight line. Okay, I'm going to draw it like this. I'm going to put little dots here to know that it carries on. It doesn't stop. Okay, and that all is restricted. We're looking just at the xy plane. The z is 0. Okay, but now let's do rewrite this, and now let's make y equals 0. When y equal to 0, then what does this equation read? X plus z equal 3. Well, that's an equation, okay, on the xz plane, right? Because y is 0. And that's going to be, if I write it in z, it'll be z equal minus x. So it's also going to be a little line going down, okay? Now it's on the xz plane, right? Now, if I'm going to do the same, and again, it carries on to the other, carries on there. Now, one last thing, you know what I'm going to make 0? I'm going to make x equal 0. In this case, I've got 2y plus z equal 3. And that is another straight line, but now on the yz plane. Okay? So what we've got here, it looks like a triangle, but remember these lines carry on. And so you can imagine that this little triangle is part of this plane, a two-dimensional plane. That carries on, it carries on. Okay? So hopefully that was a little, not a proof, but giving you an convincing that an equation with 3 variables is simply a plane. Okay, let's move on. All right, guys. Okay, so I'm a little bit disappointed. I was going to play with my visualizer, and I can't get it to work. So sorry. So instead, we're gonna just have to use a file that some document that I saw on the web, and also I can see it's doing this. Oh, right, no, the colors. I don't know if the colors are right. I think the colors are not right, but well, it will have to do. What we're doing in this part, stand here. What we're doing in this final bit of the lesson, we're trying to look at the geometrical representation. What does it look like actually visually? Equations. What do the equation with 3 variables look like? And more importantly, what their solution or not having solution. And like I said, it's a bit more fancy stuff, and I'll be honest with you, I haven't seen these kind of questions in the exam, but you never know. So I mentioned it to you before, the equation with 3 variable, okay, you can see ax plus by plus cz equal r. So instead of giving a number, I mean, it could be 2x minus 3y plus 4z equal 1. Really, it's a plane. It's a plane, okay, in the 3-dimensional. It's a 2-dimensional shape in a 3-dimensional space. But now what happens when we have a system, okay? So we can have a linear system of 3 equations like that. Well, let's start with the first one. I'm going to just stand here, okay? Right. If I have a linear system, okay, 3 equations, each equation is represented by a plane. The nice thing, a nice linear system will be where each, each plane, okay, all the planes intersect in one point, okay? So that really is the case when the determinant of that system, the determinant of the matrix is not equal to 0, okay? We've got 3 planes, they intersect in a point, we have a unique solution. Okay, so that's a well-behaving linear system. Let's move on to our next possibility. Okay. Well, in this case, we have 3 parallel planes. Okay, each equation gives us a plane, but they're all parallel. Where in this case, they're never going to intersect each other. So you probably guessed right. And what we have here is no solution. I'm not going to write it. Okay? There's no solution here. There's no solution, right? Because there is no joint x and y that satisfy all these equations. Okay, you won't be surprised also to know, you should be able to tell me that the determinant of the system, if I wrote a linear system that described by that, the determinant must be 0. Okay, otherwise there would have been a unique solution. Now here I'm going to push a little bit forward. Again, I haven't really seen questions like that, but you never know. It would be nicer if we can recognize a linear system to look like this without solving everything. And I'll show you an example. Let's say x plus y plus z equal 2. Okay? Now, if I double this equation, what will I get? 2x plus 2y plus 2z equal 4, right? But if instead of writing 4, let's say I write 1, then these equations, okay, it can never be satisfied, right? Because if I take the first equation, double it by 2, okay, 2x plus 2y plus 2z must be equal to 4, okay? But it's not. It's equal to 1. So these two planes are parallel to each other, okay? You can see it. Just like in the two-dimensional space, we looked at that x plus y equals something, 2x plus 2y equals something else, which is not double. Okay, there we two parallel lines. Here we have two parallel planes. And then we can add another one. Let's say minus x minus y minus z. I multiply this one by minus 1, and then I get, I don't know what, 3. Okay? So these will be 3 parallel planes. No solution. Determinant is 0. Okay. Now, there's another option, and unfortunately I don't have it here, so I can't draw it to you. So imagine, forget about this one. Okay, we've got 2 planes, okay, 2 planes. So it will be, let's say, 2 equations, 2 planes, and 1 plane that intersect them. So another plane that just intersect that. Okay, so we've got basically 2 planes and 1 plane that intersect both of them. It doesn't have to be in right angle, it can be 2 angles. In a different angle. Now in this case, also there's not going to be any solution. Oh, I've got a picture here. Unfortunately, I can't use the visualizer. Do I have a picture? Yes, here we go. So just, this is what I'm talking about. It's in your book actually, so you can look at, we're in page 143. All these pictures are in page 143. So you can see here, you can see this, we have 2 planes and parallel and 1 intersect them. And again, there is no one point where they all intersect each other. Each 2 planes are intersect, but the 3 don't. So again, we have no solution. How can we, what kind of system like that would look like what kind of system would it look like? So these 2 planes are not parallel. Now I can add another system, x minus 2y plus z equal 3. That is not parallel to any of those, because I didn't double or I didn't time. When do 2 equations parallel to each other? And when one is timed, when you can go from one equation to the other by timing it, by a scalar, okay? So this is obviously not parallel to any of those, and so, but these are parallel, so we have that system of, we've got a situation of 2 planes and a plane intersecting both of them, no solution. Okay. What else am I moving? All right, I've got one more. I think I had a picture of it. Here we go. So this is another case of no solution. And obviously there's no solution here. There's no one place where all these planes are intersecting. But none of them are parallel. None of them are parallel, okay? They're all intersecting, but let's look at these 2 planes. They intersect on this line, but the thing is this line is parallel to this plane. So again, there's no solution. What does this look like? Well, that's quite difficult, okay? And we don't need to go into it. But it suffices to say that if you have a system, let's say you have a linear system, that as I showed you before, you show that there were no solution because there was a row of, let's say, 0, 0, 0, and 2. Okay, so definitely no solution. But when you look at it, you can't see any 2 equations are parallel to each other, okay, then it must be like that. But like I said, I've never really seen a question in the exam where they ask you, explain what do these planes look like, which one are they intersecting or not intersecting and all that stuff. So obviously none of that. Right, now we're moving on. So these were all the possibilities of no solution. I'll just show you here in the book, okay. So we're looking at, So we're looking at this one, two planes, parallel plane intersecting, three parallel planes, and three not parallel planes, but the intersection of every two plane is parallel to the other plane. Now we're moving on to the infinite solution. So what's our first one? Okay. So infinite solution, there's again a few possibilities. We can have three planes, okay? None of them are parallel. They're all intersecting, but the intersection is not on a point. The intersection is a line. The intersection is a line, okay? And when we had an example before, let's say 1, 2, 3, 4, and this was 1, 1, and 2, and this was 0, 0, 0, 0, that's going to be one of those. That's going to be one of those. I don't want to get to kind of exactly explain why, but I did show you that the Z can be any Z. The Z can be anything. Okay, so we'll just call it Z. The Y will be some kind of function of Z. In this case, it will be, well, here we go, I am explaining it. So that will be Y plus Z equal 2. So Y will be equal to Z, or 2 minus Z. And then I can have another function for, so X plus, let's solve it. Come on, can't stop. Okay, X plus 2Y. Okay, what is 2Y? Is 2 times 2 minus Z plus 3Z equal 4. So basically I've got X, Y, and Z, okay, are equal to some kind of function of Z. So Z, well, it's just Z. It can be anything. It can be anything. That's a degree of freedom. Y is some function of Z, 2 minus Z. And X is also some function of Z. I'm not going to say, but something to do with Z. Okay? So that's a straight line. Okay? But there's other options as well. I don't know if I have them here. I don't. Okay. I don't have them here. I don't have. Yeah, okay, right. So I'm just going to pause here and go back to our book. So there's another possibility of infinite solution, which is not a straight line, okay? And that is, for example, this. X plus Y plus Z equal 1. 2x plus 2y plus 2z equal 2. Okay? 3x plus 3y plus 3z equal 3. Okay? Well, you can see that each equation here, well, they're all the same. They're all the same. Each equation is a plane. So each one of these are planes. They're not just parallel to each other. Yes, they are parallel to each other, but they are actually identical to each other. So we have three planes on top of each other. Infinite solution. The solution is not just a line, like it was in the picture I just showed you. It's actually a plane. So there's more degrees of freedom. But that's going too far now. I'm going to stop here. Otherwise it just gets